Let me ask you something strange. What if I told you that reality doesn't exist until you look at it? Not metaphorically, literally. That sounds like mysticism. It sounds like philosophy, but it's not. It's physics, and it's called quantum mechanics. Now, people often think quantum mechanics is about tiny particles, electrons, photons, atoms, but that's not what it's really about. Quantum mechanics is about how nature behaves when you stop pretending it makes common sense. When people hear the word uncertainty, they usually think it means confusion. They imagine bad measurements, clumsy instruments, human ignorance. That's not what this is. Quantum uncertainty has nothing to do with us being sloppy. It's not that we don't know enough. It's that nature itself does not provide an exact answer. Imagine you're watching a tiny particle, an electron. You ask two very reasonable questions: where is it, and how fast is it moving? In everyday life, those questions are trivial. A car has a position and a speed. A ball has a position and a speed. No mystery. But in the quantum world, the universe quietly says, you may ask one question clearly, but not both. If you measure the position precisely, the speed becomes fuzzy. If you measure the speed precisely, the position dissolves into a blur. Not because the particle is hiding information from you, but because there is no exact information to hide. This is the key idea, and it's subtle. The electron does not have a perfectly defined position and speed at the same time, not secretly, not behind the scenes. Those values simply do not exist simultaneously. Reality itself is spread out. This built-in blur is what we call the uncertainty principle, first clearly formulated by Werner Heisenberg. But don't let the word principle fool you. This isn't a guideline. It's not a limitation of technology. It's a rule the universe follows every single time. Harry's another way to think about it. Before you look, the particle isn't sitting at one precise point waiting to be discovered. It's more like a cloud of possibilities, not ignorance possibility. When you measure, you don't just reveal reality. You force reality to choose. And this is where people start to feel uncomfortable, because we like a universe that runs like a machine. Predictable, exact, certain. But quantum mechanics tells us something unsettling. The universe doesn't need certainty to function. It runs perfectly well on probabilities. This doesn't mean the universe is chaotic. It means it's subtle. It doesn't commit to exact values until it must. It keeps its options open. And the moment you demand an answer, it gives you one. Just one. So uncertainty is not confusion. It's not failure. It's a window into how reality actually works. Not fixed, not frozen, but constantly becoming. And once you truly accept that, quantum mechanics stops looking crazy. It starts looking honest. Now let's take the next step. If uncertainty made you slightly uncomfortable, this part will make you pause. Because here, reality does something very strange. It refuses to choose. In everyday life, things are definite. A coin is either heads or tails. A light is either on or off. A door is either open or closed. Nature behaves politely, but in the quantum world, politeness disappears. Take a single particle, an electron. You send it toward two possible paths. In our normal thinking, it must pick one, left or right, this or that. But quantum mechanics says, no, the electron takes both paths at the same time, not halfway, not quickly switching, both. This state is called superposition. Now be careful. This does not mean we don't know which path it took. It means there is no single path. The particle exists as a combination of possibilities, a spread-out description of what could happen. Reality hasn't made up its mind yet. This is not poetry. It's math. It's experiment. It's repeatable. And it works every single time. But here's the unsettling part. The moment you try to check, the moment you ask, which one did you choose? The superposition collapses. The particle suddenly behaves as if it had chosen all along, but it hadn't. Your question forces an answer. This idea bothered many great physicists, including Erwin Schrödinger, who created a famous thought experiment to show how absurd this feels when scaled up. But the absurdity isn't the point. The point is this: nature allows multiple realities to exist simultaneously until interaction makes one real. People often ask, so is the particle really in two states at once? The honest answer is, stop trying to imagine it like an object. Quantum mechanics doesn't describe things the way we used to. It describes possibilities, and those possibilities behave as if they are real. Because mathematically they are. This is where many explanations fail. They try to force quantum behavior into classical pictures, but nature doesn't care what pictures you prefer. As Richard Feynman put it, the universe doesn't explain itself in words. It behaves, and we do the best we can to keep up. So, superposition is not magic. It's not particles being indecisive. It's reality operating at a deeper level than certainty. Before measurement, the universe does not commit. It explores. It waits. And only when interaction becomes unavoidable does reality settle on a single outcome. And once you truly accept that the universe doesn't choose until it must, you're ready for the next shock. Because sometimes two distant things seem to know about each other instantly. Now we arrive at the part that made even great physicists uneasy. Because here, the universe does something that seems impossible. It ignores distance. Imagine two particles created together, not close, not touching, together. Their properties are linked from the very beginning. You send one particle far away, across a room, across the earth, across the galaxy. The other stays with you. Now you measure yours. Instantly the other one knows, not after a signal travels, not after time passes, instantly. This connection is called entanglement. At first people thought this had to be wrong, because it violates common sense. And it deeply bothered Albert Einstein, who famously called it spooky action at a distance. He believed something must be missing, some hidden information, some secret message carried along. Because how could reality allow this? But nature had other plans. Careful experiments were done, again and again and again, and every time the universe answered the same way. No hidden signals, no delayed communication. The particles behave as if they are one system, no matter how far apart they are. This isn't faster than light messaging. You can't send information this way. But the correlation is real. When one particle chooses an outcome, the other one doesn't decide. It already agrees. Here is the quiet, unsettling idea. Entangled particles are not two separate objects. They are one shared reality spread across space. Distance doesn't break the connection because distance was never fundamental to begin with. This was formalized by John Bell, who showed that if quantum mechanics is correct, then reality cannot be both local and classical. Something we deeply believe about the world has to be wrong. And experiment shows. So what does entanglement really tell us? Not that the universe is magical, but that our idea of separation is incomplete. Space is real. Distance is real. But at a deeper level, relationship comes first. The universe is not made of independent pieces. It's made of connections. And once you see that, uncertainty makes sense. Superposition makes sense. Quantum mechanics stops being strange. It becomes consistent. Uncomfortable, but consistent. So entanglement is not a trick, it's a clue. A clue that reality is not built from objects, but from relationships that cannot be torn apart. And that realization changes everything that comes next. Now we come to the question everyone asks. Is light a wave, or is it a particle? It sounds reasonable, it sounds scientific, and it is the wrong question. In everyday life, things fit neatly into boxes. Waves spread, particles collide. Water is a wave. A rock is a particle. Simple. But quantum mechanics doesn't respect our boxes. Light sometimes spreads out, interferes, overlaps just like a wave. Other times, it arrives in tiny, discrete clicks just like particles. So which is it? Wave or particle? Nature's answer is quiet but firm. Stop asking. This becomes unmistakably clear in the double-slit experiment. Send light through two tiny slits. Don't watch it too closely and you get an interference pattern, a wave behavior. Now try to observe which slit the light goes through. The pattern disappears. The light behaves like particles. Same setup, same light, different reality. This is not light being sneaky. It's not playing tricks. It's doing exactly what the equations say. The behavior depends on how you interact with it, not what it really is. Here is the deep lesson. Wave and particle are human ideas. They are models, descriptions, tools. Nature never promised to fit inside them. As I explained, quantum mechanics does not tell us what things are. It tells us what happens when we perform experiments. And that's enough. So when you ask, is light a wave or a particle? Quantum mechanics replies, it behaves like a wave when you treat it like a wave. It behaves like a particle when you treat it like a particle. And it refuses to be either when you demand certainty. This isn't ambiguity. It's honesty. Nature is not confused. We are because we insist on classical pictures in a non-classical world. Wave-particle duality is not a paradox to be solved. It's a warning label. It tells you, do not mistake your descriptions for reality. The universe does not owe you an intuitive explanation. It only owes you correct results, and quantum mechanics delivers those results with ruthless precision. So uncertainty wasn't confusion. Superposition wasn't indecision. Entanglement wasn't magic. And wave-particle duality? It's simply nature reminding us that our questions are sometimes too small for the answers. So after all this strangeness, after uncertainty, superposition, entanglement, after waves that act like particles and particles that act like waves, what is quantum mechanics really about? Here is the surprising answer. It's not about tiny things. Quantum mechanics is about how nature delivers results. Not pictures, not stories, not what is really happening behind the scenes. It is a rule book that says, if you set up the experiment like this, here is what you will observe, and here is the probability. That's it. This is what makes quantum mechanics so honest and so unsettling. It refuses to invent comforting images. It does not say, here is what the electron is doing when you're not looking. It says, here is what you will get when you look, and remarkably, that's enough to build the modern world. People often want more. They want certainty. They want a mechanical story. They want the universe to behave like a clock. But as I emphasized, nature is not obligated to be simple, only correct. Quantum mechanics doesn't describe reality the way we wish it were. It describes reality the way it behaves. Here is the deep shift. Classical physics assumes the world exists in a definite state, whether you look or not. Quantum mechanics says reality is not a list of facts. It is a list of possible outcomes. And measurement is not passive. It's an interaction. When you ask a question of the universe answers, but only in the language of probability. This doesn't make reality subjective. It makes it relational. What happens depends on how systems interact with other systems. Not on belief, not on consciousness. Just interaction. So quantum mechanics is not mystical. It doesn't say thought creates reality. It says something far more precise: outcomes are real. Predictions are probabilistic, and the universe does not commit early. Once you accept that, the weirdness fades. Uncertainty becomes natural. Superposition becomes expected. Entanglement becomes inevitable. Quantum mechanics stops being bizarre. It becomes inevitable. So what is quantum mechanics really about? It's about letting go of the demand for certainty while keeping absolute precision. It's about learning that nature is not built from solid objects, but from relationships, interactions, and probabilities that produce results with stunning accuracy. And that's the final twist. Quantum mechanics feels strange, not because the universe is broken, but because it's more subtle than we ever imagined.